Today I will talk about this new phase that we found in manganese silicide at low temperatures. And you will see how we arrived to predict theoretically something in the low temperature area of the phase diagram, and then how we, by doing experiments with neutrons, magnetometry, muons, etc., how we are trying to understand what is the origin or the origin of this B phase. Okay. These are the collaborators in this study. You can see here Inoue Sensei, but also Kojima from Triumph, Oishi from Cross, Yusuke from Osaka Metropolitan University, Miguel, who was my student, Victor, he the theoretical calculations, and Mito Sensei in Kyushu helped with the macroscopic characterization together with his student Okuma-kun. You can see here there is a big collaboration between Zaragoza, including University and Spanish National Research Council, this institute, Cross, Triumph, Osaka Metropolitan, etc., and KITE. This is the outline of the presentation. I will try to introduce our motivation, why we arrived to discuss on this phase, then the theoretical model that describes these cubic Dzyaloshinskii-Moriya interaction magnets. I will try to be a little bit provocative, showing when we can apply this model, where we cannot apply the model. I'm experimentalist, and we need to theoreticians and experimentalists, we are working together, but we need to know which are the limits of the theory, I want to say. Because sometimes the theory sometimes not every time, theory has a limit. And then we need to know. And then in this sense, I will try to be a little bit provocative. Then I will describe the experiments. You will see the theoretical model will produce some prediction that then we are going to see experimentally and we will interpret. Then we are in a chiral center, and what is a chiral structure? A chiral magnetic structure. And then all of you knows that we can, magnetic helices are chiral objects, and then this talk is related with this kind of objects. Conical helix is a helix in which also you have a ferromagnetic component along the chiral axis. Then with this, if the Dzyaloshinskii-Moriya interaction in this case, or if the propagation vector of the helix propagate in only one dimension, we can form, depending how we apply magnetic field to this structure or not, we can form chiral soliton lattices if the magnetic field is applied perpendicularly to the chiral axis, or we can form, even by increasing the magnetic field, even we can isolate chiral solitons. If the helices propagate in 3 dimensions, we have cubic helimagnets, and in this model, we can form skyrmion lattices, and even we can isolate skyrmions. Then with these isolated skyrmions, and also with these single chiral solitons, these objects have been proposed as good objects to produce magnonic devices. For example, here you can see that with skyrmions, it has been advanced that they can be used in ultra-dense racetrack memories, and we can do magnonic with this chiral solitons and form logical gates, transistors, etc. This is a nice reference in which you can see how to use these objects to produce magnonic devices. And then these objects are very interesting by two important points. They are topological nature and solitonic nature, and they are chiral objects. Then these two properties confers that these objects are robust and that means that they are protected and the chirality gives interesting properties like non-reciprocity. And then for that reason, these are very important and promising objects in spintronic and magnonics. Okay, today we are talking about physics of these objects, and we are not interested how to use in spintronic and magnonics, but they are interesting. Then motivation, which is our motivation to study manganese silicide, who we know that produce solitons and helices, etc. Motivation was we wanted to study the stability of the magnetic textures, and in particular to understand the role of the temperature in the stabilization of these stationary points is synonymous of magnetic texture, solutions of the Euler-Lagrange equations. And in particular, to understand the phase diagram of manganese silicide, in which, as Inoue Sensei told you, we can find a kind of A phase, which is formed by a chiral solid, a skyrmion lattice. Manganese silicide is a cubic helimagnet in which we have helices propagating, depend where you are applying the magnetic field, but propagating a ferromagnetic field along the four main diagonals in the cube. Then this is the first time that the temperature was included in the analysis of this, in the theory of these objects. Till that moment, the cubic helimagnets and the uniaxial helimagnets were not studied, including the temperature in the calculations. Theoreticians solve the Hamiltonians, but at zero temperature. And here we wanted to see what happened when you include the temperature, because all the experiments are done at final temperature, 30 Kelvin, 29 Kelvin. This is not zero temperature. And then you will see later that at zero temperature it's impossible to find skyrmions. Then this was our main goal at the beginning. And the stability, what is the stability? Even at zero temperature, the solutions of the Euler-Lagrange, the stationary points, can be unstable solutions. The derivative of the energy has a zero, but they are not stable solutions. We need to see that when you are moving a little bit the solution from the equilibrium point, you are going back to the equilibrium point. That means it's an unstable solution. If you are in a maximum of the energy and you move a little bit your solution, you will lose the state. Then let's go to see this first. Important. We can have helices originated by the Dzyaloshinskii-Moriya interaction, in which you have a kind of competition between an interaction, the Dzyaloshinskii-Moriya, that wants to order the spins or the magnetic moments 90 degrees, and you have the competition with the exchange interactions that wants to order parallel or anti-parallel the spins. Then the competition of both will produce this kind of helices in which the pitch angle is related with the ratio between the Dzyaloshinskii-Moriya and exchange interaction. In this case, one enantiomer is transformed in the other one, for example, by mirror plane, and one enantiomer has different energy than the other. Usually, what is happening is in the crystal, you have, because this is magnetic structure, this is a magnetic enantiomer, one of each other, but in your crystal, you have domains from both chiralities. And then each domain, each nuclear domain will use one of these helices. If you have both nuclear chiralities, at the end you will have both magnetic enantiomers. But in the case you have only one crystal with only one hand, then you will observe only one helix propagating. We did experiments in the past, and we demonstrate that many chiral crystals are formed by chiral domains, and every chiral domain has only one helix of this. If you arrive to have only one enantiomer crystal, you will have only one of these. But you can form also helices coming from competition of next neighbors interactions. There is a kind of frustration. Like, for example, you have J1 and J2, more or less the same order of magnitude, and then with this scheme, you can have symmetric helix. Symmetric in the sense that the Hamiltonian is symmetric under this transformation. That means that the angle will not change when you are changing the symmetry, when you are applying the inversion to the Hamiltonian. In this case, the angle is related with the ratio between the exchange constants, G2 and J1. Usually, the periodicity in this case, in the symmetric helix, is shorter than if you are considering, for example, a skyrmion with a very short radius, maybe it's coming from here, and if the radius is very large, maybe it's coming from here. Different interactions. But this is very important because if you don't have a long period, you will see later some approximation cannot be maybe done. In one dimension, let's start in one dimension. We have this helix, and the Hamiltonian that describes this helix is here. We have in the discrete model, we have an exchange interaction term, the Heisenberg term, the Dzyaloshinskii-Moriya. This one to align parallel or anti-parallel the spins. This one to align 90 degrees the spins. We can include one anisotropy that in a given direction, and the Zeeman term. And this Hamiltonian describes very well what is happening in the uniaxial helimagnets, for example, chromium niobium disulfide, in which if you apply the magnetic field parallel to the helical axis, this axis, you will form a kind of cone that at the end, it will produce a phase transition called instability phase transition. This is the language of Dzyaloshinskii and the Jens. The Jens was the first one working on this, and Dzyaloshinskii, because as Inoue Sensei explained, this model is similar to mathematically to the model that described the liquids, how do you say, the liquid crystals. Then, if you apply the magnetic field perpendicular to the chiral axis, that means like this, then you will have a nucleation phase transition. Both cases, at the end, for enough large magnetic field, you will have a ferromagnetic state, but in one case, the mechanism is you are closing a cone, and then it's an angle that is going from 90 to 0, and in the other case, is a period who is going for a given value to infinite. This can be seen in this example. Then, this is the chromium niobium disulfide, uniaxial helimagnet. And then here we have the helix. It's very long range helix. You can see here many unit lattices are needed to form the period. And then if you apply the magnetic field perpendicular to the chiral axis, this period is becoming large and large, like this. And at the end, you will have one ferromagnetic system because the period is going to infinite. However, if you apply the magnetic field parallel to the chiral axis, you are closing this angle, you are closing the cone, and you will end up also with a ferromagnetic system pointing along the chiral axis. In this case, is instability, and in this case is nucleation phase transitions. We were working on this in the 10 years ago, and we described what happened in these uniaxial helimagnets when you apply the magnetic field in an arbitrary direction. Because this point and this point was already described by the Jens and Dzyaloshinskii, but they didn't know what was happening when applying the field in any arbitrary direction. It was clear, it was anticipated that three critical points should be expected, because here we have instability phase transition, and here we have nucleation phase transition. Then both mechanisms are not connected. That means that in the middle, a discontinuous transition line should be expected. This is the phase diagram for a given anisotropy and for zero anisotropy. Also, if you apply the temperature, you can see how the phase diagram is changing from the zero temperature to a given temperature. Okay, then knowing this model, this uniaxial, to solve the problem in the uniaxial helimagnet, people is going to the continuum. That means they are assuming that the variation from one spin to the next one is small. Then, if this is true, if the skyrmion is radius, or if the wavelength of the object is large. That means considering the uniaxial model and in the continuum, and going to describe it in the cubic system, because now we are thinking to do some theory to describe what is happening in manganese silicide. But manganese silicide is a cubic helimagnet. Then we need to generalize this, okay, in the continuum limit, and considering propagation of the interactions along the three directions. Then this gradient term is coming from the ferromagnetic, from the Heisenberg interaction, and the Dzyaloshinskii-Moriya term produced this term here. Here we didn't put anisotropy, and this is the Thiemann term. N hat means a configuration of the spin with modulus 1. The spin and everything is included here in the energy here. Then everyone is doing like this. Everyone is considering a density of energy like this with a field, classical field, N hat, which is basically is the magnetization, modulus 1. With this, we have this Q, which is related with the periodicity, and the energy also related with Q and the spin. We are allowed to do this if the spin from site 1 to site j is the change is small. If not, we cannot go to the continuum limit. If we are considering objects coming from frustration of interactions, in which the spin is changing strongly from one point to the other, maybe this cannot be applied. Even if everyone apply, then this is something to think. Maybe we are doing a theory that this cannot be applied to explain things in which we are considering frustration of interactions. However, if we are using the Dzyaloshinskii-Moriya, usually this is the periodicity is very large. That means that from one spin to the other, the spin is changing smoothly, and the continuum limit is allowed, is possible. If you know this, you need to calculate the partition function. That means it's a kind of sum for all the configurations, the exponential of the energy divided by kBT here. And then once you have the partition function, the free energy, now in the free energy we included the temperature, which was our goal at the beginning, to have the temperature here. This is we can write, it's very easy to write, but it's very difficult to solve. And then to solve this expression, because this is a functional, this is a field, and this is a kind of integral for all the fields. The energy depends on the field, and then we need to do this kind of functional integration. And then we use the saddle point expansion. That means we will approach the partition function by the value for which the energy has a minimum. And which is the idea behind the saddle point expansion? The idea is that the term in which this is a minimum will be the largest term contributing to the integral. For example, consider 10 to the minus 10 is 10,000 times smaller than 10 to the minus 1. That means that once we are a little bit far from the minimum, from 1 to 10, this term contributes quasi nothing. Then we will do this kind of approach here, saddle point expansion of the partition function. And then we need to find where the energy has a minimum. But where the energy has a minimum is N naught. That N naught is a field describing an stationary point. An stationary point is a solution of the Euler-Lagrange equations. That means ferromagnetic structure is an stationary point. The helical structure is another stationary point. And the skyrmion lattice is another stationary point. Then, for all these three stationary points, we can find the partition function. And then at the end, we will do a kind of Taylor expansion of the energy around each stationary point. But to do this Taylor expansion, you will see we need to impose something. Then the points for which the energy has a minimum, these are called stationary points, ferro, chiral, skyrmion lattice. Maybe there are others because we know some solution of this equation, but maybe there are other solutions. And then we will develop around each solution. We will expand around each solution. Then the configuration, the idea is N naught means the minimum. And then you move out of the minimum. This movement is N hat. And N hat is basically N naught plus two fields. N naught, the minimum, plus two fields here. And it is N hat. This is the fluctuation. We are moving a little bit at each point in the crystal, the field. And then we have this N hat. This is the idea. And then if you do like this, the energy is the energy in the minimum plus the first derivative, but the first derivative is 0, plus something related with the second derivatives of the energy respect to the fluctuations. And then here it appears an operator that I will describe later, that is the K operator, that is a kind of, is telling you the secondary, is a kind of Hessian matrix of this field. And then if you have the energy, the free energy is described like this: one term, three level in the language of field theory. And then here, this is what the so-called one loop term, which include Gaussian fluctuations and something at higher order terms. Then we have one expression for the free energy. For the free energy, and then let's see what is K operator. K operator is the second variation operator, is here, it's a very complex operator, but what I'm interested to tell you is that it depends on each stationary point. don't forget, we want to determine the stability of each stationary point, the first point, and then what is happening when we include the temperature. N0 is each stationary point. And then this operator depends on N0. And if we want to do this kind of development, we need to impose that the eigenvalues of the second variation operator must be positive. And this will ensure that we are really in a minimum of the energy. If not, we cannot the Taylor expansion. And then we need to calculate lambda as function of the magnetic field. And also, we will see lambda will be function of the magnetic field. And when we will find the free energy, also the temperature will appear. And then with this, we will be able to build the phase diagram. Then the procedure. We study stability of the stationary points. That means we need to find the values of the K operator, the eigenvalues that are positive, to be sure that we are in a minimum for each point of the phase diagram. Then, once we have this, we know that the solutions are stable. And then once we know that this solution is stable, we need to compute the energy. And then the lowest energy will be the ground state. And if there are several stationary points with that are stable, one will be metastable and the other one will be the ground state. Okay. Then here we have the stationary points. N0 can be a ferromagnetic solution, or a conical helix is enough to change here, or an skyrmion lattice, describe it like this. Then we have three different stationary points. And then we compute the stability, and then we calculate the free energy, and then the energy. By doing like this, we can find this phase diagram. Below the red line, the system, there are at low magnetic field, only the chiral helix is stable. In this area, if you repeat the things for a skyrmion lattice, you will see that eigenvalues never ensure stability. A ferromagnetic state never will be stable at low magnetic field. This axis is temperature. If for magnetic field higher than this gray line, only the ferromagnetic state is stable. It's clear. And first important point, we found that the skyrmion lattice was stable in this low temperature part of the phase diagram. This was the first time, theoretically, we found that the skyrmions can be stable at low temperature. And in fact, you can see here, we don't know, in this area, we don't know which is the skyrmion or chiral. We don't know because calculations were not done under the same metric. And then in this area, we didn't know which skyrmion or chiral was the ground state. And we found here one area of the phase diagram for which ferromagnetic was unstable, skyrmion was unstable, and chiral helix was also unstable. Considering this cubic Hamiltonian in the continuum limit, only with one spin, that means when you are going to the continuum limit, you are doing a kind of microscopic model. You are not at atomic structure, you are doing a kind of macroscopic model. Okay, then compute, I explain this. And this is an unknown state. You can imagine that we wanted immediately to go to see which is the structure here. But before, we were very happy because here in Japan, Nakajima sensei published at the same time that our paper, in 2017, they published it. They did a very nice example in manganese silicide. They take a crystal here, and they put two wires in order to pass a current on the crystal. And then I will explain this experiment because it's a very nice experiment. This is the phase diagram in manganese silicide with the so-called A phase. Then they stop at 28 Kelvin, 0.2 Tesla. That means here, this point. And they measure with SANS, small angle neutron scattering. They measure, and with the configuration, magnetic field parallel to the incoming neutron beam and parallel to the 111 axis. In this case it's 001, but manganese silicide can form skyrmions along the along different directions. They found this 6-fold pattern is typical picture for skyrmions, and nothing in the perpendicular configuration. That means that there are no helices here in this point. Then they went slowly from this point to this point here, and they found 12 Kelvin, 02, skyrmions disappear, and they have only helices here. And then they apply a pulse of current. They hit the sample very fast, and they cool down. But they cool down passing through the skyrmion lattice, and they trap skyrmions at low temperature and also helices. Then this is in very good agreement with our prediction, because here, in fact, a skyrmion is metastable at low temperature. If you wait, you will have only helices. But this is in very good agreement with our prediction. 1 year later, group in Germany found, and this was published in Nature Physics, found also in copper oxide selenide the same behavior. And they say that this was neither observed experimentally or theoretically. Of course, 1 year before, it was our paper and the Nakajima-san paper. By doing something similar, also we were able to understand how thermal fluctuations can stabilize the skyrmion lattice around the paramagnetic phase. We did this theoretical calculation without temperature, with temperature, and then this was also in good agreement. And then let's go now to see the experiments. Second motivation is every time manganese silicide has been explored, has been measured, studied for, let's say, not so low temperatures. Then our calculations were in this part of the phase diagram. And we found here something that we don't know. What is this? Question mark. We know that this is not a chiral helix like the one described by this model, the one described by this sample model. This is not skyrmions here. They are not skyrmions, and it's not ferromagnetic. And then this was the second motivation. Let's explore the low temperature area in the phase diagram. And then let's do magnetometry experiments, small angle, and muon spin rotation. Then we fabricated 3 different samples, and we oriented each sample. We know for each sample which are the A axis, B axis, and C axis. And we know also for each sample the 111 direction, the 110, etc. Or we know all the main directions. And then we measure by applying the magnetic field parallel to 111. This is called sample C. And we observed that at low temperature and high magnetic field, high respect to the ferromagnetic state, from 5,000 Gauss to 6,000, we observed an anomaly in the AC magnetization. And this anomaly was independent on the frequency. You can see that it's very difficult to observe. But our Masaki Mito sensei, our colleague, he was able to find a small variation in the AC magnetization. However, considering other orientations, we don't see the anomaly. You can see here, we don't see this anomaly. And this was reproducible, for example, considering other sample and change the orientation on the same sample, you were not able to see. Also, in the skyrmion lattice area, 29 Kelvin, the in-phase magnetization has a strong signal that is not observed in the low temperature anomaly. And in the skyrmion lattice area, the out of phase has a strong absorption that is not observed in the 2 Kelvin temperature. That means that the anomaly is different from an skyrmion lattice. Okay, we know that the skyrmions are not stable there, but two important points. Our model was very simple model, was for only one spin, and in the continuum limit and cubic propagations. Very simple model. Manganese silicide is much more complex. And in our model, we didn't include anisotropies. Then maybe anisotropy should be included like a perturbation in our model, because the experiments for this phase, experiments tell you that it exists anisotropy, because we observe in one direction but not in the others. Then the model needs to be updated. We know it's not correct to describe this. Maybe anisotropy must be included later. Okay, then this is considering all this data, we found something here. This is what we call B phase. Then the theory brings us to study this B phase. This B phase, what is the origin of this B phase? Well, why we have this anomaly only in the 111 direction when magnetic field is applied along 111? However, skyrmions are observed in all the directions, but not this. And then we are people expert in large-scale facility techniques. And we did SANS and muon spin rotation. And then SANS, we perform SANS experiments in Taycan instrument in JPark, in MLF, which is a very good instrument. And also at ILL, at D33 at ILL, which is also a very good instrument. Both are very good. Maybe for these experiments are the best in the world. And we use a very large single crystal fabricated by Kosaka-san. And you can see here the single crystal, which is oriented. We know the orientations of the crystal, and we can go down in temperature, and we can apply a magnetic field, parallel, perpendicular, etc., in order to do the experiments. And also we use a single crystal to do muon spin rotation in Tryon, Tree University Mason facility, which is located in Vancouver. It's a big scale facility in Vancouver. And Here is the spectrometer M15. And here we worked with Bob Covid, with Oishi-san, and with Kojima-san. And then, before, I don't know if you are familiar with SANS. Maybe this slide, I will explain a little bit. When you have helices with a propagation vector, you can see here in this direction, if you want to observe by small angle neutron scattering, you need to locate the propagation vector of the helix perpendicular to the neutron beam. This is the propagation vector, which is parallel here. And then in this configuration, these 2 points we call satellites. The distance to the center is telling you the periodicity, the period. And the period is telling you the pitch angle. And then this is the configuration to observe helices. Chiral axis perpendicular to neutron beam. If you apply magnetic field here, you will close the cone, and the intensity of these 2 points will disappear because you are reducing the component that is turning. If you want to observe a skyrmion lattice, you need to put the chiral axis, or in this case is the perpendicular to the screen axis, parallel to the incoming neutron beam. And magnetic field, you need magnetic field to form skyrmions. And you need a magnetic field parallel to the, in this case is perpendicular to the screen, and you need to apply parallel to the incoming neutron beam. With this configuration, you will have 6 points because the lattice is hexagonal, but if you have a square skyrmion lattice, you will find only 4 points. This number of points depend on the symmetry of your lattice, okay? And then these are typically the 2 configurations that we use to describe and to find the skyrmions with SANS. And here are the experiments at 2 Kelvin, 28 Kelvin, with magnetic field parallel to the 111 direction. And parallel, this is the crystalline direction, and then parallel to the incoming neutron beam, that means skyrmion's configuration. We don't see at low temperature any signature of skyrmions as we increase the magnetic field. However, if we put the 111 direction perpendicular to the incoming neutron beam, we observe these 2 satellites that are related with the main diagonal 111, and we observe other satellites that are related with other main diagonals, 1, 1, minus 1, there are 4. But for this orientation, we were able to observe this. These points are multiple scattering of these 2. What that means? That at low temperature ferromagnetic field, our system develops helicoidal domains aligned along the main diagonals. If you don't apply magnetic field, your manganese silicide have 4 different helices propagating among the 4 main diagonals, along the 4 main diagonals. When you increase a little bit the magnetic field, this point is going back here, and this is going there. That means that you are reorienting the magnetic domains toward the 111 direction in which you are applying the magnetic field. And the intensity of these peaks increases because the size of the magnetic domain along 111 is increasing. Then the intensity increases and the other points decreases. You start now increasing the magnetic field and you start to close the cone. You have an helix, single domain crystal, and helix propagating along 111. You increase magnetic field and you start to close the cone. then the intensity decreases, and in the ferromagnetic state, you don't have any intensity. And when you are going back from the ferromagnetic state to zero, for this configuration, you don't see nothing, it's clear. But at the end, you end up with a single domain helix at ferromagnetic field here. At the very beginning, you have 4 domains. If you do this kind of hysteresis cycle, you end up with only 1. If you do the same in the skyrmion lattice area, 28 Kelvin, with 2 configurations, we can see that in this parallel configuration, we can find the skyrmions here, only with a 402 magnetic field, and then nothing. And the 4 diagonal domains are also developing, and at the end, you have only 1 diagonal domain. And at the end, at this 28 Kelvin temperature, you recover multiple domains. You don't have only 1 single domain. You recover the same. Remember the phase diagram. I will put later. You can do the same for other directions, and the behavior is similar. We observe helices, periodicity, but we don't see skyrmions. We don't see skyrmions at low temperature. We see skyrmions only at 28 Kelvin. That means that SANS experiments are not telling us too much things. The periodicity SANS are telling that there are not skyrmions at the low temperature. But our SANS experiments are compatible with helices. We have helices and kind of helices. But you will see in the discussion what kind of helices. Then let's go to do muon spin rotation experiments. I don't know if you are familiar with muon spin rotation. With muon spin rotation, you implant muons in your material. The muon is, in this case, is muon positive. The muon will go to sit in a given point in your material in which the charge is favorable. That means minimum negative charge because muon is positive. And then after a few microseconds, the muon will decay. But the muon, before decaying, is precessioning along the magnetic field distribution in the point, in the position where the muon is implanted. And then before decaying, the muon is precessioning, and when it decays, this precession will produce that the positron that is coming from the decay is not the same in one direction that in the other. The number of positrons going in one direction is different from the number of positrons going in the other direction. And then if I put 2 detectors, one in front to the other, up, forward, backwards, up and down, left and right, I can see different asymmetry functions that is related with the magnetic field distribution in the point where the muon was seated. This is the idea. Then in manganese silicide, now we need to think in atomic structure. The muon will be implanted in the 4A Wyckoff position, XXX. That means along the main diagonals. Here, black points are the points where the muon will be implanted. Well, this is the view if you look along 111. There are one here and the others are there. Then, in this configuration, for example, PY, these 2 detectors, applying magnetic field along here, along Z, crystal axis 111 parallel to this H to Z. And then in this configuration, this is a typical configuration for transfer field muon spin rotation because polarization is perpendicular to the transverse field to the field. And then muon is coming here, you implant, it starts to precession, and then these two detectors will give you this amount, this polarization. And it is related with the local field in the position of the muon. You do like this, and you observe this kind of asymmetry function as function of time. And doing the Fourier transform, you have the field distribution for each side as function of the local time, and for different temperatures. And then you can imagine, then the first big point corresponds to the local field distribution in the H1 position. In this case, is the one parallel to the magnetic field. X is X, and the other three muon sites are responsible of this second peak. And then we can do experiments by scanning, for example, this area of the phase diagram. And we want to see what is happening in the magnetic field distribution along this area, increasing the magnetic field. And we see this diagram, these curves. At ferromagnetic field, okay, ferro will be here, 0.1 magnetic field, 0.2, 0.3, etc. We observe an asterisk that is related with the applied magnetic field, because you apply one external magnetic field, and then the muon is sensible to the external magnetic field plus the fields related with the magnetic structure in the crystal. Then the idea here is how to model the fields coming from each magnetic structure in the crystal. And then let's go to think. Proposed magnetic model. The micromagnetic models cannot be applied because here the muon is sensible to each manganese site. We cannot take in micromagnetism, you are taking a volume, you take the average, and you assign to that volume a given average. Then, and then this volume, the magnetic moment for this volume is changing from one volume to the other. This is micromagnetism. This is related with a continuum limit. Micromagnetism is useful when your spin is modulus is fixed in modulus and is changing along the crystal. Then here is not the case because we muons need to know the magnetic field coming from each manganese atom and from each spiral structure or helical structure, etc. Then this is not possible. Then how to attack this problem? Then the first thing is to think which are the symmetry allow magnetic structures in this compound. We use representational analysis. For this, we need to know the space group, P213. The position of the manganese is also along the main diagonals, and the propagation vector, which is delta, 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 1, 1, 1, parallel. And then with this, you can go to the tables, or you can go to Basireps, or you can go to Sara or Carep or another software, or by hand, you can do by hand, and you can determine the magnetic representation and how this magnetic representation for this position is decomposed in irreducible representation. And then your magnetic structure will follow one of these. There are three possibilities. Or the three manganese atoms are located 120 degrees in one layer, and in the main diagonal is pointing perpendicular to this layer, or you have one layer of 120 degree or arrangement, and the second layer also 120 degrees arrangement, or you have one ferromagnetic layer, and in the other also ferromagnetic layer, but rotating a little bit. Symmetry allows these three models. And this angle is not fixed by symmetry. That means that this is not the angle telling you the periodicity of the helix. This angle is related on the phase of one helix respect to the other. Each one of these, this, and this, in this case are parallel, and each one from one layer, from one unit lattice to the other unit lattice, will form a helix. In this case, the three helices will be ferromagnetic, and the other atom, this one, will form another helix with the same period, but with a shift respect to the others. And then with muons, I anticipate we were playing with this angle because this was model to explain our muon data by allowing the variation of this phi angle. This was not possible, and this was not possible. And then only by moving only one parameter, the phi angle, we were able to fit all the data along the at 2 Kelvin, up and down. We were able to fit more or less, and then the results are here for different temperatures, but at low temperature, we observed a kind of tendency, a trend that this phi angle, it seems that it increases a little bit in the area where we observe the anomaly. And then this is not this model cannot be described by the model that I told you at the beginning, because the model, the theoretical model, the modulus of the magnetic moment is fixed, was fixed to 1, but doesn't matter, it's fixed. And here, the fact that you are moving the angle between the helices produce that the modulus of the average 4 spirals is changing. And then this is described by the theoretical model. Then it's not surprising. But experiments tell that maybe there are a kind of maybe this is you can see the error bar is large. Why the error bar is large? Because as you apply magnetic field, the component that is rotating decreases. And then obviously the error bar will increase because your signal every time is small and small. Then it's not surprising, error bar are very large. We are in this point. And then you can see here, the model is, you have these layers, and then along the 111 direction, the orange layers are forming a spiral with the same periodicity that the blue layers. And between the orange and blue is a kind of shift. This model will be compatible with SANS, with our SANS experiments, because the periodicity is the same, it doesn't change. All the helices propagate with the same periodicity, then the SANS experiments, no problem. And then if we want to calculate theoretically the intensity of the SANS, we see as function of the angle, we see that the angle, the rotation angle is producing very small change in the intensity, not visible in our experiments. This is the theoretical calculations are the black points. But we are right to fit our SANS curve very well with this expression. Then, just to conclude, we analyze the role of the thermal fluctuation. We anticipated the existence of the skyrmion lattices. This simple model, we know the limitations of the model. This model gave us the idea to explore the low magnetic field, the low temperature part of the phase diagram. We went there and we found something. This something we know that cannot be described by the model. We know the limitations of the model. And what we observed, we call phase B. Suns and moons are telling us that our data are compatible with a rotation of the helices at low temperature. And then I can tell you even more information. We collected muon data in the skyrmion lattice and in the so-called A phase. And this data can be fitted easily with a model considering 4 helices. We don't need to form skyrmion. But we need to think more on this because it should be a very important result. We need to think other possibilities. Science is not something easy. It requires time. And with this, I thank you for your attention. Thank you very much. どうもありがとうございます。